Okay, so this research, as told, is already it's about using material of unknown or also variable geometry in a real-time robotic fabrication process. So first of all, why doing this effort when we actually have very standardized products of almost any material at hand? Well, highly sophisticated tools such as robots open up the possibility to intervene much earlier in the material processing chain. And the question is more, could this be more efficient, for example, considering sustainability, but also allow new ways of designing? And especially if we are using natural materials such as timber, which are obviously quite variable in natural form. So in recent years, there has been a growing interest in this research question. So, for example, here in a series of workshops done which were looking at, for example, the scanning of branches and then trying to retrieve actually, first of all, the information from them in a simplified way. And then using this information to, on this right chart, combining simple branches without actually cutting them into grid structures. As already shown this morning, this has been also developed a step further, so into actually building real structures out of branches which were uncut and then just detailed at some parts with robotic milling of connections and then a well, let's say more manual arrangement into a structural arch. Here in the Mind is Scrap project from the company Certain Measures of Tobias Nolte and Andrew Witt, the idea was to scan waste material and computationally find the largest usable area in order to clad given design volumes. So this study combines the techniques of scanning, recombining, and robotic assembly in a continuous real-time robotic fabrication process. We investigated the use of randomly sized raw timber panels for a water-resistant envelope of a two-story timber structure. So I will introduce the material and its specifics, explain the design space we investigated in terms of geometric adaptability, variation, and analysis, and obviously show the fabrication process and its resulting demonstrator project. This was done in a master's program at, as mentioned already before, in ETH Zurich in the framework of the NCCR Digital Fabrication. And also here it's important to, of these kind of very large-scale projects, to name the people who worked on this, especially in the design and fabrication team. You can read the names, and there were also multiple NCCR chairs involved in it, mainly grammatical research, but also the Block Research Group and Professor Aber of the Sustainable Construction Department. So, going on the material, the ancient method of splitting timber panels has several advantages. First of all, the fibers are kept intact, and also then if the panel gets wet, it can dry much more easily because of a larger and more structured outer surface. And also, if you want to use as much material as possible, you have to accept a variable size, which comes out naturally out of the size of a tree, depending where the splitting occurs, as you can see on the right image, for example. This diagram shows the design space we investigated with 3 design goals. So first of all, the cladding should be adaptable to doubly curved surfaces, while remaining visually and geometrically consistent. And we also thought it would be interesting for once to have a pavilion or structure which is actually waterproof and where you can stand underneath when it rains. And also we wanted the facade to attach directly to the primary structure without additional substructures. In the following slides, I'll explain a series of studies which look at the relationship between the structure, the pattern typology, surface typology, and also the water permeability. So obviously, if you include randomness, you have a large amount of possibilities for patterns. You have multiple ways of overlapping, but also orienting of the elements. And this multiplies, obviously, when you introduce randomness. Since we had a diagonally braced substructure, we included horizontal as well as diagonal patterns. Here you see a horizontal fixation pattern with a width and height variation on spherical, doubly ruled and simply ruled surfaces. And the mapped colors you see underneath indicate here just the maximum distance between panels and the driving surface. The next images show, in contrast, a digrid pattern, also with a width randomization and angle smoothing on flat, spherical, and ruled surfaces. The variation here of the vertical overlaps causes surface ripples already, as you can see on the flat surfaces, and can cause very large irregularities on the curved surfaces. And despite being this obviously being visually very attractive, this is not ideal for creating a water-resistant cladding system, depending on the general surface inclination. So if you actually want to test physical or actual permeability in practice, as some of you might know, facades are actually only tested on real physical mock-ups. And computational simulation is still quite rarely used. But this study, for example, from Kevin Tan uses animation software, which has been becoming more and more precise in recent years for a highly detailed water intrusion test. So why not use this for scientific purposes? So we created actually a test app using the software RealFlow. This software has the advantage that it can be programmed or interfaced via Python. And we created a custom particle tracing by a Python script. This allowed detecting the particles traversing the panelized surface. And we used around 300,000 particles for each of the test samples. The goal was to analyze the water permeability in relation to the variation, overlap pattern, surface topology, and inclination. This chart on the left side shows the percentage of leak particles in relation to the width of the adjacent and overlap panels, panel height, row height, and drive surface geometry, and inclination of over 30 different surface samples. The analysis shows that the angle, first of all, obviously has a quite dramatic impact on the permeability. And it also shows that some of the elements which are, for example, just adjacent and have a randomization of the heights, it creates holes, and obviously this becomes then a quite permeable surface. It also shows that if you look on the bottom line, that the height overlap can be increased by around 50% without a significant increase in permeability if a vertical and horizontal overlap is used at the same time. So this was the pattern we also chose for fabrication. So how can you integrate a panel variability in a real-time robotic fabrication process? First of all, you need to constantly read and write data on the robot controller with an external PC during the fabrication. Therefore, we integrated the ABB PC SDK with Grasshopper Python in order to do that. And we used the following steps. So first of all, we actually remeasured the already built structural components in order to minimize fabrication tolerances. And then during the fabrication, each panel gets separately scanned. The info gets sent back to the PC to calculate a new position, and then back to the controller to perform the assembly. The information needed for fabrication were only the fixation elements of the general structure. The structure was composed out of over 4,000 different timber slats, which form a spatially braced structure, a kind of truss, which allow to adapt seamlessly between serving different functions such as a wall, slab, roof, or staircase, for example. The distances you can see between these outer bracings were adapted to fit with the maximum panel length for fixation. The scanning was done in a quite simple way. We used a light reflex sensor combined with search movements of the robot in a defined coordinate system to deduct the panel sizes. That meant also that we didn't need to do any image processing on it. It could be performed very fast. You will see it later in a short video. It basically just happens during the approach movement for picking of the gripper. For the gripper, we used a vacuum gripper, which was flexible, attached with springs in order to adapt to the rough surfaces of the shingles or panels, and 2 nail guns for fixation on the structure. Each of the components, as you can see there, were prefabricated already with the facade and transported on the site, and then combined and plugged into the structure. And also, since every part was different, assembly errors were practically impossible because they can just fit in one place. And this is here a view of the upper floor. And we had, on the opening of the AAG conference last year, over 30 people dancing on the second floor, which was quite a stability test. It's not the topic of this talk, but we dimensioned it for Swiss standards, so snow load, safety values, and everything, and also like dynamic loads, of course. So I'll show a short video for that. Oh, sorry. You see the process for the structure. There was a CNC saw integrated with the robot controller, so it can cut any angle of the flat. Cut the first part and the second part, and it gets assembled correctly. The approach movement, and that was already scanning. Yeah, so in this project, we analyzed the geometric and functional performance as water permeability through computation, and integrated the scanning, design calculation, and robotic assembly in a continuous real-time fabrication process. And we also integrated the ABB PC SDK in a custom interface in Grasshopper Python, and which can also be used for actually simulating virtual controllers. We assembled over 4,000 different structural timber elements and around 2,600 differently sized wood panels. And the total production time for this was around 5 weeks, including the prototype tests. It's also currently actually exhibited for a second time at the Design Biennial in Zurich. So I think in general the research on this topic of integrating variable or randomly sized elements in construction is still at the beginning, but I think there's a great potential, especially when you consider sustainability. It enables to use local materials directly, and this already reduces the ecological footprint of construction enormously. And also a range of natural materials can be considered, such as, for example, bamboo, straw bale, also low-grade or recycled construction materials, which I think all could have great potential for digital building processes. Also note on complexity, I think it's clear that if you increase the randomness of the used material and its geometry, it can create an enormous complexity in the computation and also fabrication. In this project, I think what it shows well is that you can use a very simple sensing techniques combined with robotic movement very efficiently. And in the future, it could also make sense to integrate, for example, quality scanning in real-time fabrication processes. So also for this purpose, I'm actually currently setting up a completely new robotic fabrication lab in Kassel, which will be able to combine subtractive and additive processes through 5-axis milling and robotic assembly, advanced sensing, and also human-machine collaboration. And so if this sounds interesting to you, I'm happy to hear from you. Thank you for your attention.